Have you ever actually wondered how artificial intelligence manages to make sense of our incredibly messy, unpredictable world? I mean, we hear constantly about complex neural networks, algorithmic trading, advanced pattern recognition. It honestly all sounds a bit like magic. But underneath all of that sheer complexity, machine learning is really just about dealing with uncertainty. And I'm going to share a little secret with you. It literally all boils down to two surprisingly simple mathematical rules.
Welcome to This Explainer. Today, we're going to demystify the core mathematical engine that's driving today's most advanced AI. We're stripping away all the heavy jargon to look at the actual foundation of probabilistic machine learning. And by the end of this, you're going to see exactly how basic everyday logic scales up to literally build the future.
So here's our game plan. We'll start with the language of uncertainty, move on to a really helpful fruit box metaphor, unpack the sum rule and the product rule, and finally, tie it all together with Bayes and machine learning.
All right, let's jump right into Section 1, the language of uncertainty.
To kick things off, we need a common vocabulary. You know, a lot of people see probability as just these scary, abstract equations. But according to our source material, it's actually a super straightforward, frequentist concept. It's just the fraction of times a specific event occurs out of the total number of trials. If you do something over and over and over again, how often does outcome A happen compared to everything else? Forget the intimidating Greek letters for a second. We are literally just counting and dividing.
Okay, Section 2, the fruit box metaphor. Let's anchor this math in a highly relatable physical metaphor straight from our sources. Imagine a red box. There's a 4 in 10 chance, so a 40% probability, that this specific box gets selected. Now peek inside. It contains 2 green apples and 6 oranges. So, if we do happen to choose this red box, the vast majority of what we pull out is going to be oranges.
Now contrast this immediately with a blue box. There's a 6 in 10 chance, or 60% probability of picking this one. So it's actually the more likely box to be chosen overall. But check out its contents. 3 green apples and just 1 orange. This box is heavily dominated by apples. So keep this mental picture in your head, right? A red box packed with oranges and a blue box packed with apples.
In the language of machine learning, both the box we pick and the fruit we draw are what we call random variables. These are simply variables whose exact outcomes are uncertain before we actually run our trial. We can denote the random variable for our box as B, which takes the values of red or blue, and we denote the fruit as F, taking the values apple or orange. By clearly defining these random variables, we're bringing those abstract x's and y's you see in math textbooks into everyday reality.
Moving on to Section 3, the sum rule.
Now that we've got our metaphor down, let's tackle the first of our 2 fundamental rules. To really grasp probability, it totally helps to visualize a grid. Just picture a grid where the columns represent the possible states of one variable, like our boxes, and the rows represent the states of the other variable, our fruit. If we run a ton of trials, we can track the instances where a specific box and a specific fruit intersect. The number of points falling into a specific cell where a certain row and column meet is denoted here as Nij.
And this brilliantly illustrates our first major concept, joint probability. Denoted as P of x, y, joint probability is simply the probability of 2 events happening together. On our grid, it's just the fraction of points that fall into a specific intersecting cell out of the total number of points across the entire grid. It's the probability of, say, picking the red box and getting an apple at the exact same time.
So, the absolutely crucial point here is this. What if we only care about the fruit, and we don't care about the box at all? What if we just want to know the overall probability of picking an apple, completely regardless of where it came from? Well, this is exactly where the sum rule comes in. To find this, which is what we call the marginal probability, we literally just sum up the chances across all the boxes. We look at the row for apples and sum up the values from every single column in that row. We are basically marginalizing or summing out the box variable to just leave the probability of the fruit by itself.
All right, Section 4, the product rule. Let's see how this builds into dealing with brand new information. Imagine I hand you a piece of fruit from one of the boxes, but I refuse to tell you which box it came from. You look down at your hand and you see an orange. The question is, given that we have chosen an orange, what is the probability that the box we chose was the blue one? Notice how knowing just one piece of information, the fact that the fruit is an orange, fundamentally shifts the odds of another. Because we know the blue box only had 1 orange in it, while the red box had 6, our human intuition immediately tells us, hey, it's probably the red box.
That intuition is formally known as conditional probability. It's the probability of event Y occurring, given that event X is already absolutely known to have occurred. Visually, on our grid, we're no longer looking at the whole board. Because we know we have an orange, we zoom in strictly on the orange row. We're now only looking at the fraction of instances within that specific row, rather than the total grid.
And notice how beautifully it all ties together in an elegant equation. The product rule dictates that the joint probability, the probability of X and Y happening together, is simply the conditional probability multiplied by the marginal probability. Simply put, the chance of getting a blue box and an orange is the probability of picking the blue box in the first place, multiplied by the probability of drawing an orange, given that you are definitely holding the blue box.
Let's lock this in by comparing them right next to each other. The sum rule gives us the big, independent picture, the marginal probability of just one variable, obtained by adding up all the other possibilities. The product rule, on the other hand, gives us the dependent, conditional picture, exactly how two variables interact and influence one another. These two rules, as remarkably simple as they seem, are the absolute bedrock of probabilistic modeling.
Section 5. Bayes and Machine Learning.
So, how did these simple rules regarding boxes of fruit scale up to actually power modern artificial intelligence? Like, how do we go from apples and oranges to self-driving cars and trading algorithms? The huge leap happens when we combine them. By mashing the sum and product rules together, we immediately derive Bayes' theorem. And Bayes' theorem is literally the foundational algorithm for how machines learn from data. It allows a machine to have a prior belief, observe new data, and immediately update its belief.
Here is Bayes' theorem in all its glory. I know, it looks complex, but look really closely. The numerator, the top part, is literally just the product rule, and the denominator, the bottom part, can be fully expressed by expanding it using the sum rule. Bayes' theorem is quite literally just the product rule divided by the sum rule. It allows us to seamlessly reverse conditional probabilities. It essentially tells a machine, hey, if you know the probability of the fruit given the box, here is exactly how you calculate the probability of the box given the fruit.
And here is where it scales so beautifully. In our metaphor, we used discrete, chunky, countable things, right? Apples and oranges. But the source material emphasizes that these exact same mathematical rules apply perfectly to continuous data as well. When we move from counting fruit to measuring continuous variables, like exact temperatures, velocities, or crazy financial prices over time, we just swap out our summation grids for calculus integrals. The underlying logic of the sum and product rules stays exactly the same, whether it's a simple bar chart or a hypercomplex continuous multivariate Gaussian distribution contour.
So why does all of this actually matter to you? Because these two underlying principles are exactly what Wall Street algorithms use to tame the sheer chaos of the stock market. It's what computational learning theory, like pack learning, uses to guarantee that a pattern recognition model will actually work on brand new data rather than just blindly memorizing the past. Every single time a system estimates an expected error rate or updates a latent variable based on new observations, it is literally just running the sum and product rules over and over and over again at blistering speeds. We've seen how the simple counting of apples and oranges transforms into the mathematical engine of the future. The sum rule maps our horizons, and the product rule essentially updates our world as new facts arrive. But it leaves us with a pretty profound thought. If the most advanced artificial intelligence on the planet is fundamentally just navigating degrees of probability using the sum and product rules at massive scale, is absolute certainty just an illusion? I'll leave you to ponder that one. Thanks for joining me for this explainer, and keep questioning the data around you.